Hi, so this is the final theorem that I want to prove about the pebble game. So this theorem says, suppose I have a pebble game state H. So this is a directed graph with pebbles on the edges, and H plus E, so the underlying undirected graph H plus E is 2, 3 sparse. Then H plus E will be accepted by the pebble game too. Okay. To prove this theorem, let me first give you a new definition. So definition, if I have a pebble game state H, so H equals VE is a pebble game state. If U is a vertex in V, then we define the reach of U to be the set of all vertices in V such that there exists a directed path from U to V. Essentially, I can follow arrows from U to V. So this is the set of all vertices that are reachable from U via directed paths. Okay. So I want to show that if I already have accepted a 2, 3 sparse graph, if the pebble game's already accepted a graph, and by our previous theorem, if it's been accepted, that's 2, 3 sparse. Then if there's another edge that I want to try to insert, and H plus E, I know it's 2, 3 sparse, the pebble game will actually accept it. Okay, so let's prove this theorem. First, let's give names to the endpoints of E. So we'll say E is the edge UV, okay? And well, the trivial thing is that, like, if it happens that in our current pebble game state H, pebbles U plus pebbles V is equal to 4, then automatically E is accepted. Okay. So what we really need, the work of this theorem is to show that E still gets accepted if the pebble game state we're given fails that. So if the number of pebbles on U and V is less than 4. Okay, so let's do this. Let's let V prime equal to the set of vertices reachable by U plus, together with, the set of vertices reachable by V. So we can maybe draw a little picture here. Here's U, here's V, the reach of U. So like there are going to be things like this. That would be in the reach of U, that stuff. There's stuff that's in the reach of V. And this, the reach of U union the reach of V, is the set V prime. Okay? So what things can we observe about this set V prime? Well, one fact is that it must be that the out degree of this set V prime is equal to 0. Okay, why is that? Well, this is supposed to be all of the vertices reachable by U and V. If one of these vertices had an out degree, if one of these vertices had an edge that started in V prime and ended somewhere out of it, what that would mean is that then that vertex, like in this case, would be reachable by U, and it would have been in the set V prime. So we'd get a contradiction. Okay, so has to have out degree 0. And let's think about this. from before we had that corollary, remember? We had the corollary that said that the number of edges in the induced subgraph on a V prime was going to be 2n prime minus the out degree of V prime minus the number of pebbles on V prime, right? If H is a pebble game, is a state in the pebble game, that has to be true. Okay, so, but I just told you that this is equal to 0. So this is telling me that the number of edges in E prime is 2n prime minus the number of pebbles in V prime. And let me see. Let me pause this for a second. Oop, I didn't want to pause the share. Let me pause the recording for a second. All right, I'm back. I realized what I wanted to say. So, okay, so that's what the corollary tells us. But what do we already know? By assumption, H prime, or by assumption, H is a pebble game state. And what we already know is that if something's been accepted by the pebble game, it's 2-3 sparse. So we know that H is 2-3 sparse because the directed graph is a pebble game state. Okay, so since it's 2-3 sparse, we know that the number of edges in E is less than or equal to 2n prime minus 3. And now we will put that together with, oh, why do I have a strict, oh, and in fact, it has to be a strict inequality. Why? Because E is independent. Okay, we know that's true because H plus E is 2-3 sparse. So when I add in the extra edge E, I have the weak inequality satisfied. Okay, so I have the strict inequality because H is 2-3 sparse and H plus E is independent. So this implies then that putting these two things together, that I have 2n prime minus the number of pebbles on V prime is less than 2n prime minus 3, or in other words, that 3 is less than the number of pebbles on V prime, i.e., for the number of pebbles on the vertices of V prime is at least 4. So what does that tell me? Well, I have at least 4 pebbles in the reach of U and V, which means I can bring those pebbles back to the vertices U and V and get at least 4 pebbles on the endpoints of U and V, i.e., we can reach 4 pebbles from U and V and can bring these back to U and V. All right, we're done for now.